Okay, let's get busy solving this problem. This is the marshmallow problem. We got to get this guy taken from his mean, scary ice state to superheated steam, hopefully with one shot of the gun. So what do we have? It's currently minus 10 degrees Celsius. That's our starting temperature. The intelligence puts that thing's mass at 50 kilograms of solid ice. Kilograms, that's the mass. We're going to have to change that to grams. I'll show you in a second. I don't want him reforming from water, so do not stop until that vapor is at 100 degrees Celsius. We just can't stop when he is boiled. We got to keep heating up that steam. So this is a 5-step problem. Go back to your heating curve to understand how we're going to do this. The heating curve looked like this, of course, and over here at the very start is where we have our Q equals MC delta T, because we're going to be changing the temperature. We're going to be going from minus 10 degrees Celsius to 0. Over here is where we're going to be warming the liquid up, so we'll need some energy there. That'll be going from 0 to 100 degrees Celsius. And finally, over here, we'll need our last heat up of the steam from 100 degrees Celsius to 180 degrees Celsius. We've got 2 other steps in there, so that's our first, or it's 3 steps, 1, 2, 3. 2 other steps we have to melt this mass of ice, and this is where we use our latent heat of fusion times our mass right there. And our final step that we got to think about is our latent heat of vaporization right there to turn marshmallow into a gas. Let's get started with this thing. Let's get some calculations rolling. Okay, let's get started with this calculation part of this problem. Before we get started with the calculations, we're going to need to go to our reference table and pull up 3 values. We're going to find 3 values for the specific heat of water. We need ice, which is 2.05 joules per gram degree Celsius. We need the specific heat for water, liquid water, which is 4.18 joules per gram degree Celsius. And we need the specific heat for steam, which is 2.02 joules per gram degree Celsius. We also need 2 more values. The latent heat of fusion, which would be H sub F, is 334 joules per gram. And we need the latent heat of fusion for vaporization, which is H sub V, which is 2,260 joules per gram. With those numbers in hand, we are ready to get started on our first step of the problem. Let's get going and heat this thing up. I'm going to do the different steps in different colors just to keep it clear. Our first step is to heat marshmallow up from minus 10 degrees Celsius to 0 degrees Celsius. So this is going to be Q equals MC delta T. To approach this, we need Q equals our mass. Our mass, remember, is 50 kilograms. But because our specific heats are in grams, we need to change that into grams. So we multiply it by 1,000. So we have 50,000 grams. So our mass is 50,000 grams. It's going to be a big clunky number, but it's a big monster. 50,000 grams times C. That C value that we want is the specific heat of water, but we want it in its ice form. So it's going to be 2.05. And our delta T, we're heating marshmallow up from minus 10 to 0. So our change in temperature is going to be just 10 degrees. Multiply that all out, we get a gigantic number, 1,025,000 joules. That is step 1. We've heated marshmallow up from minus 10 to 0 degrees. Step 2, we need to melt marshmallow, turn him from the solid form into a liquid form of water. For that, we're going to use Q equals the heat of fusion times the mass of marshmallow. Again, our mass isn't going to change. It's going to be 50,000 grams, but we need our heat of fusion from our reference table, and that is 334 multiplied by 50,000. Whoa, 50,000 There we go. Multiply this, again, we get a pretty large number. It's going to be 16,700,000 joules. That is step 2. Think back to the heating curve. We're on step 2. So we need that number in there as well. On to step 3. Step 3, we are heating the liquid up. We've turned Marshmallow into a big old pile of water. Now we need to heat them up to the boiling point of water, so we're changing the temperature again. We'll need our formula that has the change of temperature in it, and that is Q equals mc delta T. Same setup as last time, however, we're talking about liquid water this time, so C is going to be 4.18 joules per gram degrees Celsius. So again, plug and chug. Our mass is the same, 50,000 grams. Big old monster. Times our specific heat, 4.18, times our delta T. Our change in temperature is going to be from 0 to 100 degrees to prepare him for boiling. So we have 50,000 times 4.18 times 100. Again, big number, big number. 20,900,000 joules. Big monsters, big number. Think back to our heating curve. This is the slanted line going up to that second step in our problem. Step 4, we've got to boil them. So we've got this big pile of really hot water. We got to keep pouring on the heat so we can boil all that away and turn the liquid into a gas. For that, we're going to apply heat using the value for the latent heat of vaporization, and that is H sub V times the mass. Again, the mass is always going to be 50,000, but looking at our reference table, we see the heat of vaporization is 2,260 joules per gram to turn water into steam, times our mass, 50,000. Just do the multiplication. Again, a relatively large number. 113 million, 113. Let me grab the eraser from up here and get that down here and get rid of that. Sorry about that. So this will be 113,000,000 joules. That is step 4. A lot of heat, little bit left. We're almost there. All right, our final step with any kind of calculation in it, we are heating the steam up to 180 degrees. It's already at 100 degrees. We need to go up to 180. We're changing the temperature, so we need the formula that says we're going to change the temperature, mc delta T. Our mass hasn't changed. It's still 50,000 grams. Our C, or our specific heat of water, now we need the value that says specific heat of water for steam. It's different from the other two, 2.02 joules per gram degrees Celsius. Plug and chug. Mass has not changed. 50,000 grams times C, 2.02 times delta T. We're going from 100 to 180. That means the difference from 100 to 180 is 80 degrees. Just multiply, and our final really big number here, 8,080,000 joules. That is our last step. That is step 5. So we've got our 5 values that we need for each step of the way. Last thing we got to do, add them all together. Last step. I've moved all the values over for each step of the way. We had 5 steps here. Step 1, heating from minus 10 degrees to 0 degrees, melting at 0 degrees, heating from 0 degrees to 100 degrees, boiling, and then heating from 100 degrees to 180 degrees. Add them all up, we get a huge number, 159,705,000 joules. That's a lot of energy. Wow. Hopefully our gun can have that much energy in it and Marshmallow won't reform and kill us. That would be a good thing. If you're working on the Iceman problem is exactly the same as this, except you're going backwards. You're releasing heat because you're starting as a thawed out thing and you're becoming frozen. So we went up the staircase of a heating curve this time. For Iceman, you go down the staircase of a heating curve, add all those values together. Take a shot at the Iceman. Can't wait to see what you get.